let's just put it this way. X plus b over 2a squared. Right, and then well, obviously an a in the front. But what have we done? We have added a term in the middle, but when that makes this expression, this changes the expression. So we got to subtract it back, and the thing we're going to subtract back is b over 2a squared multiplied by a because there's an a in the front, and then adding the c. So in the end, this expression will become alright, does that look any familiar? This is the vertex of a quadratic function at its minimum. This is the value of a quadratic function, the y value at its minimum. So if you go like one step further from this, you'll get the quadratic formula. So hopefully this is understandable. I'm just going to give you a discrete example now. But actually, so this expression right here will translate into one of those quadratic forms inside of a square root that I wrote down earlier. It depends on the value of c, b, and a. So if this sign turns negative, we have the form x squared minus 1, and then we're going to use the substitution sec theta. If this is positive and a is also positive, then we have the expression x squared plus 1, and we're going to use the substitution tan theta. Now if a is negative and this is positive, then we're going to use the substitution, we're going to see the form 1 minus x squared, which we're going to use the substitution sine theta for. So again, this is very relevant to what we were doing before. Now let me just show you with an example. Let's just directly skip that. Integral of x plus 1 square root over square root of 5 plus 2x plus x squared dx. So first step, again, as we see this quadratic expression with a linear term in the middle, is we're going to complete the square. In this case, it's very easy because x squared plus 2x plus 1 is x plus 1 squared, and then we'd add a 4 at the very end. So this integral will translate into x plus 1 over square root of x plus 1 squared plus 4. Right, so we're going to use the trigonometric substitution. Recognizing this as a form x squared plus 1, we let, actually one more step before we do that. X plus 1 square root of x plus 1 over 2 squared plus 1, the entire thing number 2. Taking out the 4, which outside of the square root will become a 2. Now using the trigonometric substitution and recognizing this as the form x squared plus 1 using tangent theta. That whatever is inside of the bracket, in this case x plus 1 over 2, be equivalent to the tangent theta. And then we're going to see that x is equivalent to 2 tangent theta minus 1, which will make dx 2 sec squared theta d theta. Continuing with this question, making the substitution, it will become x plus 1, which is 2 tangent theta over square root of x plus 1 over 2 squared, which is tangent squared theta, plus 1, there's a 2 in the front, and then multiplied by, we substitute dx equivalent to that entire expression down there, which is this. And that will become, to cancel. So a tangent theta, 2 in the front because there's 2 here. C squared theta, entire thing over C theta d theta. C squared and C cancels out. This gives me integral of 2 tangent theta C theta d theta. All right. Okay. So, I'm not sure if you still remember what I just erased. The list of common trig integrals. The integral of tangent theta secant theta is just tangent theta plus c. All right, so just we're going to pretend that we don't remember this though, and let's see how more complicated it can get because I'm going to illustrate that there's a third level of substitution that we're going to make. So this is going to be equivalent to 2 integral of sine theta over cos squared theta d theta. We're going to let w be equivalent to cos theta, and dw will be negative sine theta d theta. So this will become 2 integral negative dw over w squared. Which becomes, let's just directly evaluate it, negative 2 times negative 1 over w plus c. All right, and finally at the end of this integration, all we have to do is just make all the reverse substitutions now. And as you can see, there's 1, there's 2, and I was expecting a third. Apparently there wasn't. Oh, okay. All right. I guess we'll need 2 over w plus c. Reversing this first substitution right here. It's 2 over cos theta plus c. Right, again, now we're reversing the trigonometric substitution. I think this is probably the hardest part, or maybe not the hardest part, but a very non-traditional step. Where we have theta here, we known before that x plus 1 over 2 is tangent theta. Let what is in the numerator be x plus 1 over this side right here, and 2 be over here. Because tangent theta is this side over this side, we have satisfied the condition tangent theta is equal to x plus 1 over 2. And this will make this entire hypotenuse here x squared plus 2x plus 5. All right, so what does that give me? Cos theta is going to be equivalent to this side over this side, which is 2 over square root of x squared plus 2x plus 5. Okay, finally making that last substitution. 2 over square root of x squared plus 2x plus 5. Okay, hold on, very, very fast. What do we do? We've gotten the final result is just square root of x squared plus 2x plus 5 plus c. Does that look any familiar? We basically started with it. So the lesson here is not only that the trigonometric substitutions can be done, but also to recognize that sometimes just because you see a quadratic form inside of a square root doesn't mean you have to use trigonometric substitution. Let's try normal substitution. Let u be equivalent to x squared plus 2x plus 5. Sorry, actually, be equivalent to x plus 1, I believe, squared plus 4. And that's equal to x squared plus 2x plus 5. Right? So what do we do? du is going to be equal to 2 times x plus 1, and that dx. So we have that the top is 1/2 du, and the bottom is just square root of u. So this integral right here can actually just directly become 1/2 of du over square root of u. And this is going to be equivalent to square root of 1 over square root of u is just u to the negative 1/2. And the integral of that is u 1/2 times 2. Right? Because we're bringing down the 1/2 and it cancels out and we get negative 1/2 on top. So that will give me 1/2 times 2 square root of u, which is just square root of u. And substituting u back, I get square root of x squared plus 2x plus 5. Wow, that was easy. Right? I actually didn't realize this when I was making this example, but afterwards realized that the answer was very simple. So I went back to figure out why this was the case. I guess it was a good lesson to learn because obviously this few lines right here, I know it's a little messy, is much faster than doing the entire trigonometric substitution. So yeah, something to know there. All right, so that's pretty much it for the trigonometric substitution. I'm going to give a few examples. I'm going to give one last example, which is not very common. Maybe something not very common you'll see. But let's just do it right here. Let's revisit the previous example, where we have integral of negative arc cos of x over square root of 1 minus x squared dx. I introduced this at the beginning as a third example for integration by substitution. And the idea is that the derivative of arc cos x is equivalent to negative 1 over square root of 1 minus x squared. So this is directly integrable using substitution. But we can also use integrate this recognizing the square root of 1 minus x squared form by letting u equals to sin theta, and du is cos theta d theta. So this integral will turn into integral of arc cos of sine. All right. Arc cos. My bad. I thought it was something wrong. But x equals to sine theta, and dx equals to cos theta d theta. And then we have arc cos of sine theta on top, and negative square root of 1 minus sine squared theta. The entire thing multiplied by cos theta d theta. Right? Now this denominator here again just turns into cos theta. But what do we do with the top here? What is arc cos of sine theta? This is what I wanted to illustrate. An example where we evaluate this using the right angle triangle again. So let theta be this angle again. We are given that x equals to sine theta. So let x be this side and 1 be here. And we know that sine is this over this, which is just x. And then sine theta is that. So what is arc cos of this ratio? Let's consider this one, this angle right here. Cosine of this angle is also this side over this side. So we have figured out what arc cos is through drawing this right angle triangle. It's just this angle right here. And that's equivalent to pi over 2 minus theta. So this is probably not something that you've seen before. But the result is going to be that we have simplified this entire expression into pi over 2 minus theta. And then the cos theta over here and the cos theta over here cancels out, and so we just left with integrating pi over 2 minus theta d theta. Right, and that's the negative sign in the front, almost forgot. which is equivalent to theta squared over 2 minus pi theta over 2 plus c. And then we can put the theta back, which I can't do yet because I have to erase this side. Putting the theta back, theta was equivalent to arc sine of x. So this will give me arc sine of x squared over 2 minus pi times arc sine of x over 2 plus c. So that's the final answer. But notice that this is different from what I got before by directly integrating it, because I said that arc cos has the derivative negative 1 over square root of 1 minus x squared. So this is just arc cos x squared over 2. So what happened? Well, these expressions are not equivalent, for sure. But what's going to happen is that these two actually differ by a constant number. And I guess I can't really tell you exactly what constant they differ by. But the point here is that using different methods of integration sometimes will get you slightly different expressions which differ by a constant, which is why we have this constant term right here. So the integral is really a family of different expressions that differ by a constant. Actually, I do have the constant right. Pi squared over 8. Sure. All right, and that's all for the trigonometric integration. Integration by parts will be the next step. Finally, something new. Yes? Yes, sir.
You go over for the trick substitution, like for trick substitution, do you have to put restriction for every question?
Yes. I know I didn't do it because I'm not a fan of putting the restrictions on, but I think as I wrote on that board earlier, you need to specify what range of theta it works.
Yeah.
But eventually, in the end, it doesn't affect the final outcome because the final outcome doesn't have anything to do with theta. The only time where you might have to be careful about it is when it's a definite integral where you have a and b, right? So you have to make sure that these two are actually within the range you specify. So yes, the answer is that you have to specify the range for theta on your exam, which I apologize for not doing.
No, I just make sure.
Correct. Yes.
How did you get from the equation on top to one after it?
Oh, right. So this is not. You mean this line to this line?
Yeah.
So I didn't get from this line to this line. This line, I had this example before as the third example to my to integration by substitution, and because arc cos derivative is negative 1 over square root of 1 minus x squared, this could directly be integrated, and the result would be this. But if I use trigonometric substitution, then the result would be this first line right here. So the point here is to illustrate that using different techniques of integration, you might result in two different expressions which differ by a constant. And in this case, the constant is negative pi squared over 8. So I'm just saying that maybe you use two different techniques, and the result you get will be slightly different. But then they're still both correct answers. All right. Integration by parts. So let's go back to Math 137 for a second again. So recall that the product rule of differentiation is the derivative of a product of fx and gx is equivalent to the sum of the derivative of the first times the second plus the derivative of the second times the first. Now, how is that relevant to the integration by parts group? Let's try integrating both sides. Let u equals to fx, and then du over dx is f prime of x, right? And then let's have v equals to gx. Then dv over dx is g prime of x. What happens when we integrate this side? We have uv is equivalent to integral of f prime of x, which is du over dx, times gx, which is v dx, because at the very end of the integral sign you need a dx, plus the exact same thing except with v replaced by u. Right, so this part right here is f of x prime. This is g of x. This part right here is g prime of x. And this part right here is f of x. Right? So the dx and dx cancel out. And what we're left with is the integration by parts formula. uv minus, and move one of these to the left side, integral of v du is equal to integral of u dv. This right here is u dv, and this right here is v du. Alright, so just to stress what it is. Now, if you have definite bounds, then so one thing that I forgot to do because my page number was messed up is that we're going to go back to integrating by substitution for just 1 second. Just 1 second. And the thing to note is that you have to be careful with the bounds of a definite integral when you're doing integrations by substitution. Because when you're seeing something like integral from 3 to 5 of 2x plus 1 over 2 dx, right? What do these two numbers mean? What they actually mean is that you're integrating from x equals to 3 to x equals to 5, right? So I know this you can do without integration by substitution, but let's take one moment and let u be equivalent to 2x plus 1 and du equals 2 dx. Then this entire thing will become integral of u over 4 du. Well, can we still write 3 and 5 right here? No, we cannot, because these are bounds for x, but we have changed the value of the variable that we're integrating. So what we need to do is we need to find out the new values of u that matches with the original values of x. So what happens when x equals to 3? U is equivalent to 2x plus 1, which is 2 times 3 plus 1 equals to 7. When x is equal to 5, we have u is equivalent to 2x plus 1 again, which gives me 11. So this integration bound right here is not 3 and 5, but rather from 7 to 11. 7 to 11, what a convenient number, right? So I just wanted to verify that these two are the same. If we integrate this way, we're going to have x squared over 2 plus x over 2 from 3 to 5, which is equivalent to, I'll just tell you that it's equivalent to 25 over 2 plus 5 over 2 minus 9 over 2 plus 3 over 2, which is equivalent to 9. If I do it this way, I'm going to get it's equivalent to u squared over 8 from 11 to 7, which is 121 minus 49 over 8 equals 72 over 8, which is 9. So these two are equivalent. And the takeaway here is that when you're doing integration by substitution with definite integrals, you need to be careful with what values the bounds, what the bounds are when you're changing variable. Sometimes when you do integrations, maybe you do a substitution and then eventually you evaluate, you're like, oh, I'm going from 3 to 5. But no, you're not, because you changed variables. Right? Obviously, what you can do is at the very end, you can reverse all the substitutions, express everything in terms of x again, and then do this. But sometimes it's just easier to do this. All right, so that, now that I got that out of the way, going back to integration background. Okay, so what's the key of integrating by parts? We want to recognize the integrand as a product of two things. Let's say we recognize it as u of x, p of x, and q of x. This is the integrand. Where one of these two is something that we can easily differentiate, and the other one is something we can easily integrate. So once we have that, we'll let u be the easily differentiable one. And then we differentiate to get du. And then we can let dv be equivalent to the integrable one. And then v will be the integral of it. So I'm going to illustrate this with a few examples again. Very simple example. Integral 4 to 9 of long y over square root of y. So the first thing to use product rule is that this function has to be a product or a quotient, obviously. Otherwise, you can't use the product. Which one of these two parts are easily integrable? We can't really integrate log y. I mean, maybe you can, but it wouldn't be done in one step. But on the other hand, we know that 1 over square root of y is just y to the negative 1/2. And the integral of it will be equivalent to negative, or rather 2y 1/2. Because this is using the exact opposite of the power of differentiation. So once we have established that 1 over square root of y is the easily integrable part, we're going to let dv equals to 1 over square root of y, and u equals to log of y. This will imply that d is equal to the integral of that, which is equal to 2 square root of y, and du is going to be the derivative of this, which is 1 over y. Right? Now we have that. Substituting the formula, uv minus integral of du, which is equivalent to 2 ln y square root of y minus integral of 2 square root of y times 1 over y. And the final result is going to be 2 ln y square root of y minus these two are going to turn into 1 over square root of y again, which then we're going to have the integral is going to be 4 square root of y. So then we just have to substitute the bonds for it. So, and 9, and the final result is going to be 6 ln 9 minus 4 ln 4 minus 4. And this, I believe, is the question 7 of your assignment number 1. I think I'm going a little too slowly here. now get to the final class.